Okay, so very welcome back once again, and we are going to continue our discussion of N-type and P-type semiconductors, basically extrinsic or impure semiconductors. In our previous module, we talked about how to make a pure semiconductor as impure, and we saw N-type. Now in this module, here we go. We are going to see how to make a P-type semiconductor. So what you see from the schematic diagram, let us say this is your standalone single crystal silicon or germanium lattice, the whole picture except the middle atom. And in this single crystal silicon or germanium lattice, you have this single atom in which this is silicon or germanium atom, and in this atom you have in its outermost orbit or outermost shell four valence electrons as shown by the dotted blue: 1, 2, 3, and 4. And obviously in the innermost orbits you have few other electrons. The total number of electrons in all of the orbits of silicon are 14. So atomic number of silicon is 14. Total number of electrons in all of its orbits for germanium atom is 32. That's why germanium atomic number is 32. So now let us say this is a silicon or germanium atom. Let's say this is silicon, four valence electrons for each of the atom. This is the second atom. This is the third atom. This is the fourth atom. This is the fifth atom. This is the sixth atom. This is the seventh, and this is the eighth. Forget about this atom for a while. So you have single crystal lattice of the silicon or the germanium, and the atoms are arranged as shown. It means in the outermost orbit, you have this valence electron that is going to form a pair or bond with the valence electrons of this atom in its outermost or outermost orbit. So that electron pairing or electron sharing is called as covalent bonds. So you can see that these are covalent bonds. These are covalent bonds. These are covalent bonds. These are covalent bonds. Okay. So with this arrangement in the single crystal silicon or germanium lattice, you have insufficient number of free electrons. When you talk about the free electrons, it means those electrons have broken the covalent bonding, and they have broken the covalent bonding, and they have liberated themselves to take part into the conduction process inside the material. However, they need an external energy such as ionization potential or a thermal energy or the energy from light to break this covalent bond. So this is the example of impure, not impure, pure semiconductor material. And there are insufficient, it means not sufficient number of free electrons available because they are tightly packed in the covalent bonds. And even if they break the bonds at the room temperature, let's say, few of them manage to break these bonds and they liberate and free themselves. So those are called as free electrons. So you can't really say this pure material or pure crystal silicon lattice or germanium lattice is sufficient enough to have to act as a conductor. Okay, to behave as a controlled conductor. That's why we call it as a semiconductor. Okay, so we want to add some impurity so that we can make it controlled conductor. So the purpose here is to make the number of charged carriers increase in the lattice. So you got this new lattice now. So what you do, as we saw in the previous model, instead we are trying to insert a foreign atom into the original single crystal lattice of silicon or germanium. So this is a foreign atom which is called as an acceptor atom. In previous we saw we added donor atom. Now this time we got acceptor atom. Now what is the speciality of this acceptor atom? So those acceptor atoms are from the materials called boron, gallium, or indium. These three atoms have this property. In its valence band or the outermost shell, these atoms have only three valence electrons. One, two, three. It doesn't have fourth valence electrons. In our previous model, we saw we could have antimony, that was a donor atom, and that had five valence electrons. But now let us focus here. We have three valence electrons, one, two, three. So what happens when you add this foreign atom into the original crystal lattice? You got new lattice atomic structure for the silicon now, or germanium. With this boron or gallium or indium, let us say this is a boron B, and rest is the blue one, this positive charge sign here. They are silicon or germanium atoms. So one electron of this acceptor atom, we'll see in a moment why it is called acceptor. So one electron from here and one electron from here, they are forming a pair. This is also forming a pair. This is also forming a pair. However, this valence electron from this silicon or germanium atom doesn't find an extra electron from the acceptor atom, for example, boron, to form a pair with. So we see that this state, this covalent bond is not complete. And this electron, void of electron or deficiency electron, is called as the empty space. So it means you call it an absence of electrons. You call it as a hole. That means this atom is always ready to accept a foreign electron to come over here. So let's say you have this electron pair acquires sufficient external thermal energy and it breaks the bond, and then it will jump right over here. So then it will create a hole over here, because that will be the empty or void state. So here it's called as void and empty states. And that's why there would be so many such atoms that will be added to this silicon or germanium crystal lattice to create a new lattice. And because of each atomic addition, you will have many free charge carriers which will have positive charges. In earlier cases, we have free charge carriers which are electrons in n-type, and that is called as n-type semiconductor. In this case, this would be called as p-type semiconductor. Okay, so impurity atom accepts free electron to the structure. So it is going to accept your free electrons. So that's how we dope germanium or silicon with the above impurity atom and insufficient number of electrons to complete the covalent bonds of the newly formed lattice. The resulting vacancy after addition of this atom is called as hole, and the resulting vacancy will readily accept free electrons coming right over here. So hope you found this model useful and you understood what is p-type semiconductor, how it is created. If you did so, share it with others, and till then stay tuned for more engaging contents like this. Till then, we